A composite number can be written as a product of two smaller numbers. If the factors are composite, they can be written as products of even smaller numbers. We can continue this process, but only for so long. Remember, a descending sequence of whole numbers must end. For example, we can try to factor 36. 36 is composite because 36 is 6 times 6. But 6 is composite, and 2 and 3 are prime, so we can't break this down any further. Our ability to factor a composite number leads to several important results. Our first important theorem about primes: every composite number has a prime factor. Now, it's easiest to work with conditionals, so let's restate this. If a number is composite, then it has a prime factor. Let's prove this. A common type of proof in number theory is known as a descent proof. This is a mix of proof by contradiction and proof by induction. It begins like a proof by contradiction. We assume the negation of what we want to prove. It continues like an induction proof. We show that if the statement is true for some set of whole numbers, then the statement is true for another set of whole numbers which are less than the original set. Since this takes us back to the initial premise, we conclude that there is another set of whole numbers even smaller. This produces a descending sequence of whole numbers which must have a last element. We get a contradiction in one of two ways: if the sequence can't continue forever, or if the last element introduces a contradiction. So we want to prove that if a number is composite, then it has a prime factor. So remember, you can always assume the antecedent of a conditional, so we'll let n be a composite number, and then we'll want to assume the negation of what we actually want to prove. So we'll assume it doesn't have a prime factor. Since n is composite, we can write it as a product of smaller numbers, where, by our assumption, neither is prime, so both must be composite. Suppose n prime has a prime factor, then n is, and so n will have a prime factor, contradicting our assumption. So n prime must also be composite without a prime factor. Consequently, if n is a composite number without a prime factor, then there must be a smaller number which is also composite without a prime factor. But this takes us to our starting point, so we can produce a descending sequence of composite numbers without prime factors. However, a descending sequence of whole numbers must have a last term, which can't be composite, producing our contradiction. Now, a useful strategy in mathematics is to consider the corollaries. So we've shown that every composite number can be written as a prime times some other number, but that other number is either prime or composite, and if it's composite, it can be written as a product of a prime and some other numbers. This gives us another decreasing sequence of whole numbers, which has to end with a product of primes. And consequently, we have the corollary: every composite number can be written as a product of primes. So 100 is prime times a composite number, which is prime times a composite number, which is a product of primes. In other words, primes are inevitable. Since every composite number has a prime factor, we can rewrite any composite number as a product of primes. This gives us the prime factorization of the number. So let's find the prime factorization of 480. And at this point, we're not committing ourselves, yet, to any properties of that prime factorization. One way to proceed is to find any factorization. And if one of the factors is prime, great. If not, we can factor it. And so we might proceed as... Now, this might seem to be easy, but factorization is actually the hardest easy problem in mathematics. it only seems easy because we've only ever done easy problems. For example, we might want to find the prime factorization of 113,507. And a major problem in number theory is how can you tell if a number is prime, and if it's composite, how can you find its prime factors? This leads us to the second important theorem about primes. There are infinitely many prime numbers. The theorem and its proof go back to Euclid, who lived around 300 BC. The usual proof is a proof by contradiction, but Euclid didn't do it this way. So the Euclidean proof begins as follows. Suppose we have a finite list of prime numbers. Consider the number that's the product of all of these primes plus 1. This number is not divisible by any of the primes, because dividing n by any of them will leave a remainder of 1. So n is either a new prime, or it's composite with a new prime as a divisor. And what we've actually proven is the following. If the known primes are some list, there's another prime, which is either the product of all the known primes plus 1, or a prime divisor of this product. Using the idea of this proof, we can find new primes. For example, suppose the known primes are 2, 3, and 5, then their product plus 1 is 31, which is prime. Now the known primes are 2, 3, 5, and 31, and their product plus 1 is, which isn't prime, but does have a prime factorization that gives us two new primes, 7 and 19. And this goes to show that proof plays a key role in mathematics. The least important aspect of proof is that it verifies something is true. But in the history of forever, nobody ever tried to prove something they didn't already believe to be true. So what's the point? The more important aspects of proof reviews what you should know, proof reveals new insight, and proof raises new questions. So here the proof of the infinitude of primes reviews key properties of divisibility and factorization, and the theorem that every composite number has a prime factor. The proof also reveals a new insight, how we can find additional primes. And it raises new questions. What primes do we discover this way? Do the primes discovered depend on our starting set? Are there primes that we don't discover? Are there primes we always discover? And so on. It's important to keep in mind, progress is driven by questions, not answers.